300 miles off the coast of Oregon, hidden under a mile of dark water, a mountain bigger than the Empire State Building is filling with molten rock. Scientists set a deadline for it to erupt. That deadline came and went. So did the next one. Something inside this volcano changed, and it broke every prediction built to catch it. We're heading down into axial seamount, home to boiling hot springs, giant tube worms, and microbes that survive on poison gas instead of sunlight. If mysteries like this pull you in, hit subscribe and dive with us. The pressure is climbing again. The old rules stopped working. Get ready, we go under now. 300 miles off the coast of Oregon, the ocean hides a mountain nobody can see. It rises from the seafloor in total darkness, cold water pressing down on every side. No sunlight reaches this deep. No ship passing overhead would ever guess what sits below them. This mountain stands almost 3,600 feet tall, close to 3 times the height of the Empire State Building. Its peak sits about 4,600 feet under the surface, and its base drops even deeper, closer to 8,500 feet down. Down here, the water is barely above freezing, and the pressure would crush a human body in seconds. This is axial seamount, an active volcano living far from anyone's backyard. It does not smoke. It does not glow on the horizon. It waits, silent and unseen, doing something most volcanoes never do this quietly. For years, scientists have kept their eyes locked on this exact spot. Not because it threatens anyone on land, because something strange keeps happening beneath the waves, and every time researchers think they understand it, the volcano changes the rules again. Picture a mountain slowly filling like a water balloon nobody can watch fill. Pressure builds where no camera on Earth's surface could ever catch it. The only way to know what is happening is to send machines down into the crushing dark and listen. And listening is exactly what a small group of scientists have spent decades doing. They built cables, they built cameras, they built an entire nervous system across the seafloor, all aimed at one mountain that refuses to erupt on schedule. Something inside this volcano is changing right now, in ways nobody fully expected. To understand why, we first need to see the shape of the beast itself, because this volcano does not look like any mountain you have ever pictured. Most volcanoes end in a point, a cone rising to a single peak. Axial seamount breaks that picture completely. At its summit sits a caldera, a wide sunken bowl nearly 2 miles across and stretching close to 5 miles long, shaped almost like a rectangle carved into the ocean floor. A caldera like this does not form the way a mountain grows. It forms the way a mountain falls in on itself. Long ago, a massive eruption drained the magma chamber underneath the summit so fast that the ground above it had nothing left to hold it up. The roof collapsed, sinking downward and leaving behind this scar. Picture a cake pulled out of the oven too early, the middle sinking while the edges stay standing. That is roughly what happened here, except the middle sank across an area the size of a small city, and the edges became towering rock walls. Those walls are no small detail. Some of the fault lines ringing this caldera rise as high as 500 feet, cliffs of solid rock standing guard around a hollow centre. Down inside that hollow, cracks split the seafloor, letting scalding water and liquid rock escape from deep within the earth. Most calderas on land are round, shaped by symmetrical collapse. This one refuses to follow that pattern too, and scientists still argue over exactly why its shape turned out so rectangular. Some blame the way magma moves sideways underneath it, a long crack stretching for miles in 2 directions. That detail matters more than it sounds. A caldera shaped like this does not just tell us what happened in the past. It tells us where the next eruption is likely to break through, since axial has a habit of cracking open along those same stretched fault lines again and again. For decades, nobody even knew this strange shape existed under the waves. It took a ship, a sonar system, and a bit of luck to find it in the first place, and that discovery changed everything scientists thought they knew about this stretch of ocean. In 1981, a survey ship crossed a quiet patch of the Pacific Ocean, dragging sonar equipment behind it to map the seafloor below. Nobody on board expected to find much. This was routine mapping work, the kind of slow, careful survey that rarely makes headlines. Then the readings changed. Instead of a flat, featureless bottom, The sonar traced the outline of a massive rise in the seafloor, a mountain nobody had charted before. It sat directly along the spine of an underwater mountain range called the Juan de Fuca Ridge, right where scientists knew new ocean floor was constantly being born. The crew named their discovery Axial Seamount, a nod to its position along the axis of that ridge. At the time, nobody could have guessed how much attention this one lump of rock would eventually receive, or how many careers would be built around watching it breathe. Early visits told researchers this was no ordinary underwater hill. Instruments picked up heat pouring from cracks in the rock. Later dives revealed water gushing from vents at scalding temperatures, carrying minerals that painted the seafloor in strange colours. Something down there was clearly alive with heat. It took years of return trips, submarines and remote cameras before scientists understood they had found one of the most active volcanoes in the entire Pacific Northwest, hiding in plain sight the whole time simply because nobody had ever looked hard enough. What makes a mountain like this rise from the ocean floor in the first place? That question sent researchers digging into the deeper machinery of the planet itself, into forces working far below where any ship or submarine could travel. And the answer they found involved two enormous slabs of Earth's crust, quietly tearing apart from each other every single year. Deep beneath the Pacific Ocean, two massive pieces of Earth's crust are pulling apart from each other, inch by inch, every single year. This is the Juan de Fuca Ridge, a seam in the planet where the Pacific Plate and the Juan de Fuca Plate slowly drift in opposite directions. As these plates separate, they leave behind a gap. Nature does not tolerate empty gaps like this for long. Molten rock rises up from deep inside the Earth to fill the space, cooling into brand new ocean floor. This happens constantly, all along ridges like this one, all across the planet. But Axial Seamount sits somewhere even more unusual than a typical ridge. It also happens to rest above a hotspot, a fixed column of heat rising from deep within the mantle, the same kind of feature that built the Hawaiian Islands over millions of years. Picture two forces working together like a conveyor belt slowly pulling apart while a blowtorch burns steadily underneath it. The ridge stretches the crust thin. The hotspot pumps in extra heat and extra magma. Together, they give this one location an unusually powerful, unusually reliable supply of molten rock. That combination explains why Axial Seamount behaves so differently from a quiet, sleepy volcano. Most volcanoes wait decades or centuries between eruptions. This one has erupted around 50 times in just the last 800 years, an almost restless pace for something buried under a mile of ocean. Scientists studying plate boundaries elsewhere on Earth often struggle to find a location this active, this accessible, and this safe to study up close. Because nobody lives nearby, nobody has to evacuate when the ground starts swelling. That safety turned Axial Seamount into something rare, a live volcano that scientists could study without fear of anyone getting hurt. That freedom to watch closely, without the pressure of protecting a nearby town, is exactly what allowed this single underwater mountain to become one of the most closely monitored volcanoes anywhere on the planet. No town sits near Axial Seamount, no airport tracks ash clouds rising from its summit, because nothing ever rises that high. An eruption here cannot cause a tsunami, cannot trigger an earthquake felt on land, and cannot threaten a single human life on shore. You might expect a volcano this harmless to get ignored. Instead, scientists treat it like one of the most important volcanoes on Earth to study, and the reason comes down to opportunity rather than danger. Most active volcanoes sit near cities, coastlines, or farmland, places where a wrong prediction could cost lives. That pressure makes careful, patient study difficult, since researchers cannot experiment freely when real communities depend on getting the warning right the first time. Axial Seamount removes that pressure entirely. Nobody evacuates if a forecast turns out wrong. Nobody panics if scientists guess incorrectly about timing. That freedom lets researchers test bold new ideas about predicting eruptions, take risks with their forecasts, and learn from mistakes without anyone getting hurt in the process. Think of it like a flight simulator for volcano scientists, a place to practice forecasting eruptions long before those same techniques get applied to volcanoes that actually threaten people. Every lesson learned here, Every failed guess, every successful prediction feeds directly into how experts might one day protect towns living beside far more dangerous mountains. That is the real reason this hidden volcano became such a big deal in the science world. It is not about protecting anyone nearby. It is about learning to read the warning signs of a volcano well enough to one day save lives somewhere else entirely. But watching a mountain buried under a mile of freezing, crushing ocean water is nowhere near as simple as watching one from a hillside with binoculars. To pull this off, scientists had to build something that had never existed before anywhere on the planet. You cannot climb Axial Seamount with a notebook and a thermometer. You cannot fly a drone over its summit or hike along its rim. Everything about studying this volcano has to happen through machines, sent down into darkness and crushing pressure, then trusted to send their findings back. For decades, that meant occasional visits. Research ships would sail out, lower instruments, collect a batch of data, then leave. Months or years might pass before anyone checked on the volcano again, leaving huge gaps in the story of what was really happening down there. Then researchers built something completely different. The world's first wired volcano observatory, a project called the Regional Cabled Array. Instead of occasional visits, this system created a permanent live connection between the volcano's summit and scientists sitting comfortably on dry land. Led largely by teams at Oregon State University's Hatfield Marine Science Center, the project turned Axial Seamount into the most closely monitored volcano on the planet, watched every second of every day rather than once every few months. Imagine trading a handful of postcards mailed once a year for a live video call running non-stop, 24 hours a day. That is roughly the leap this project made possible, turning a distant, mysterious mountain into something scientists could watch breathe in real time. Instruments across the seafloor now capture earthquakes the moment they happen, measure how much the ground rises or falls, and stream video from cameras trained directly on the volcano's most active vents. All of it travels instantly through cables running along the bottom of the ocean. This kind of constant watching had never existed for any volcano before, anywhere in the world. To make it possible, engineers had to solve an enormous problem. How do you send power and data across hundreds of miles of open ocean without anything failing? Beneath the waves near Axial Seamount runs a network of cable stretching roughly 660 miles, snaking across the seafloor like a nervous system built for an entire underwater world. Every signal, every warning, every flicker of activity travels along these lines back to shore. Connected to that cable network sit more than 140 separate instruments, spread across the volcano's summit and slopes. Seismometers listen for the faintest tremors. Pressure sensors track the ground, rising or sinking by fractions of an inch. Hydrophones capture sounds no human ear could otherwise hear. One high-definition camera stays locked on a single hydrothermal vent nicknamed Mushroom, streaming footage non-stop from beneath 1,500 meters of water. Scientists sitting in an office can watch shimmering, superheated water pour out of the seafloor in real time without ever leaving their desks. Picture threading a stethoscope, a thermometer, and a camera directly into the chest of a sleeping giant, then leaving them there permanently so doctors never miss a single heartbeat. That is essentially what this cable network does for an entire underwater volcano. This constant stream of data does something no occasional ship visit ever could. It lets scientists watch patterns build slowly over months and years, catching subtle shifts that would be impossible to notice with only a handful of scattered visits. And those patterns eventually revealed something remarkable. Buried in years of pressure readings and earthquake counts, researchers began noticing the same signature repeating itself before each of the volcano's eruptions, a fingerprint hidden inside the noise. That fingerprint would eventually let scientists attempt something no one had ever pulled off for an active volcano before, predicting exactly when it would erupt months ahead of time. But first, the volcano itself had to show its hand not once, but 3 separate times. Since scientists began tracking it closely, Axial Seamount has erupted 3 times. In 1998, in 2011, and again in 2015. Each event offered a fresh chance to study exactly how this volcano behaves in its most dramatic moments. The 1998 eruption began with a swarm of earthquakes clustered right at the volcano's summit. Within hours, that shaking began marching outward, spreading south along a crack in the seafloor called a rift zone, stretching for miles as a molten rock forced its way through solid rock. Unlike volcanoes on land, none of this produced fire, ash, or a single explosion. Axial seamount is what scientists call a shield volcano, built from thin, runny lava that oozes out gently rather than blasting skyward. Picture pancake batter spreading slowly across a hot pan instead of a firework exploding overhead. That gentle style of eruption matters enormously. It means no shockwave, no tsunami, and no danger racing toward the Oregon coastline. The lava simply spreads across the seafloor, cooling into fresh black rock, quietly reshaping the volcano's summit far below any ship or coastline. The 2011 eruption followed a similar pattern, catching researchers partly by surprise with how quickly it struck. But it also proved something crucial. The volcano's cycle of filling and emptying was not random. It seemed to follow rules one's patient scientist might eventually learn to read in advance. Then came 2015, an eruption unlike the other two in one enormous way. This time, researchers were not caught off guard. Months before it happened, a small team of scientists had already gone public with a bold, specific prediction, staking their reputations on a mountain nobody could see or touch. That prediction would either prove volcanic forecasting could work, or it would fail spectacularly in front of the entire scientific community watching closely. What happened next changed how researchers everywhere thought about predicting eruptions, and it started with a bet nobody was sure they could actually win. Months before 2015 began, geophysicist Bill Chadwick and his colleagues made an announcement most scientists would have considered reckless. They stated publicly that axial seamount would erupt again, and they attached a rough time frame to that claim rather than leaving it vague. Predicting a volcanic eruption months in advance sounds almost impossible, and for most volcanoes it still is. Even today, researchers usually cannot say more than a volcano might erupt sometime in the coming years, offering little more than an educated guess dressed up in scientific language. But Chadwick's team had spotted something unusual in years of data collected from the seafloor. Before the 1998 and 2011 eruptions, the ground had swelled upward by roughly the same amount each time, before finally breaking loose. A repeating threshold seemed to exist, buried in the numbers. If that threshold held true a third time, the team reasoned, they could actually watch the ground rise toward it and call the eruption before it happened, rather than simply explaining it afterward the way scientists usually do. In April of 2015, the ground finally reached that threshold, and axial seamount erupted almost exactly as predicted. For the first time in recorded history, scientists had successfully forecast a volcanic eruption in advance, using nothing but patterns in swelling ground and shaking rock. News of the success spread fast through the scientific world. Here was proof that volcanoes were not entirely unpredictable chaos machines. Somewhere inside all that shaking and swelling hid a rhythm, and researchers had finally learned to read at least one small piece of it. That victory came with a heavy price attached, though nobody fully realized it at the time. A successful prediction does not just earn praise, it sets an expectation. Having called one eruption correctly, Chadwick and his team now faced enormous pressure to do it again, using the very same volcano that had just made them famous. To understand why that next prediction turned into such a headache, we first need to understand exactly what swelling ground really means, and why a slowly rising seafloor works as such a powerful warning sign in the first place. Deep beneath axial seamount sits a chamber filled with molten rock, slowly refilling after every eruption drains it. As magma pours back in, pressure builds inside that chamber, and the ground above it has nowhere to go but up, rising by tiny amounts, day after day, year after year. This process is called inflation, and it works almost exactly like blowing air into a balloon. At first, nothing dramatic happens. The surface stretches slightly, almost too small to notice. But keep adding pressure long enough, and eventually that surface has to give way somewhere. Pressure sensors scattered across the caldera floor track this rise with startling precision, detecting changes measured in fractions of an inch. Combine that with the number of small earthquakes rippling through the rock, and scientists get two separate clues pointing toward the same underlying story. As magma pushes upward, it stresses the surrounding rock, cracking it in thousands of tiny places. Each crack sends out a small earthquake, often too weak for any human to feel, but easily picked up by sensitive instruments listening around the clock. Picture squeezing a stress ball tighter and tighter. At first it simply compresses, but keeps squeezing, and eventually the material inside starts to strain and crackle under the pressure. That straining, translated into rock and magma, is exactly what earthquake swarms represent beneath a swelling volcano. When inflation and earthquake activity both climb together, following the pattern seen before past eruptions, scientists gain real confidence that another eruption is approaching. It becomes less about guessing and more about recognizing a signature the volcano has shown before. But inflation only tells half the story. Once a volcano finally does erupt, all that built-up pressure has to go somewhere, and the ground that spent years slowly rising does not simply stay in place. What happens next reveals just how violently a swelling volcano can let go all at once. When axial seamount finally erupted in 2015, the chamber of molten rock sitting beneath its summit emptied out fast, sending fresh lava spreading across the caldera floor. With all that material suddenly gone, the ground above the chamber had nothing left holding it up. Within hours, the caldera floor dropped by roughly 8 feet, an enormous collapse happening almost instantly compared to the years it had taken to slowly rise. Instruments recording the seafloor's height captured a sudden dramatic plunge, as if the ground itself had exhaled all at once. This process is called deflation, the mirror opposite of the slow inflation that built up for years beforehand. Picture letting the air out of that same balloon in one sudden burst, rather than slowly over time. The shape collapses almost instantly once the pressure holding it up disappears. Sensors scattered around the caldera recorded this collapse in extraordinary detail, tracking exactly how fast the seafloor dropped and where the change was strongest. That data gave scientists an unprecedented look at what happens the instant a volcano releases years of built-up pressure in one violent moment. For the animals and ecosystems living on axial seamount's summit, this collapse was not some abstract number on a graph. Fresh lava spread directly across parts of the caldera floor, burying vents, reshaping the landscape, and wiping out pockets of life that had taken root there. Yet something strange happens after a collapse like this. The volcano does not simply stay flat and quiet. Almost immediately, the same forces that caused the eruption in the first place begin working again, refilling the empty chamber below and setting the entire cycle back into motion. Watching that rebuilding process unfold, slowly at first, gave researchers a rare front-row seat to an entire volcanic cycle, playing out from collapse to recovery. And what they saw over the following decade would eventually set up one of the biggest scientific predictions this volcano had ever attempted. After the 2015 eruption drained its magma chamber and dropped the caldera floor, axial seamount did not simply sit empty and still. Almost immediately, fresh magma began flowing back in from deep below, and the long, patient process of refilling started all over again. Picture a lung slowly drawing breath back in after a hard exhale, expanding bit by bit rather than snapping back all at once. That is roughly how this recovery worked, with the seafloor rising steadily over months and years, rather than jumping back into place overnight. Instruments connected through the cabled observatory tracked every inch of this recovery in real time, recording the ground's slow climb back toward the height it had reached before the last eruption. Scientists watched the numbers tick upward, month after month, patiently building towards some future threshold. This stretch of quiet refilling might sound uneventful compared to a dramatic eruption, but for researchers, it represented the most valuable data of all. Every inch gained told them something new about how fast magma was flowing back into the chamber below, and how the volcano's internal plumbing actually worked. At times, the pace of this rise sped up or slowed down, sometimes rising by several inches a year, other times crawling forward far more slowly. Those shifts hinted that the volcano's magma supply was not perfectly steady, but instead ebbed and flowed in ways nobody fully understood yet. By comparing this new inflation data against records from before the 2011 and 2015 eruptions, Scientists searched for the same repeating threshold that had made their 2015 prediction succeed. If that pattern held true again, they might be able to call the next eruption too. As the years rolled on, the numbers climbed closer and closer to that magic threshold, and excitement began building right alongside the swelling seafloor. By the end of 2024, researchers were staring at data suggesting something big might be only months away. By late 2024, something remarkable had happened beneath the waves. The seafloor above Axial Seamount's magma chamber had risen back to roughly 95% of the height it reached just before the 2015 eruption, edging closer to that critical threshold with every passing month. For scientists who had spent nearly a decade watching this slow recovery, that number felt electric. 95% meant the volcano stood right on the edge of repeating its old pattern, teetering close enough to the breaking point that an eruption suddenly felt like it could arrive at any time. At a major scientific conference that year, researchers presented their findings to a room full of colleagues, laying out the data and daring to suggest a timeframe once again. Based on how quickly the ground was still rising, they proposed a window stretching from the middle of 2024 through the end of 2025. That announcement rippled far beyond the conference hall. News outlets picked up the story of an underwater volcano quietly building toward eruption just off the American coastline. And for a while, Axial Seamount became an unlikely topic of public fascination, an invisible mountain suddenly impossible to ignore. Underneath all that public attention sat the same careful math that had worked once before. Track the inflation, track the earthquakes, compare both against the patterns seen in 2011 and 2015, and estimate when the ground might finally cross that familiar threshold again. Confidence ran high. The pattern had worked before. The numbers looked eerily similar to what preceded the last eruption. Scientists had already proven once that they could call this volcano's next move in advance, and everything pointed toward doing exactly that a second time. But volcanoes rarely make things that simple. Just as the countdown toward 2025 felt like it was locking into place, the ground beneath Axial Seamount began doing something scientists had not fully planned for, quietly breaking away from the very pattern that had made their earlier predictions so successful. With inflation data pointing so clearly toward the old threshold, scientists felt confident enough to make a bold public promise. Axial Seamount would very likely erupt before the end of 2025. This was not a vague guess buried in a research paper. It was a specific public deadline. Setting a deadline like this carries real weight in the scientific world. Researchers do not attach their names and reputations to a guess unless the underlying data feels genuinely strong. And based on everything the cabled observatory had recorded, the pattern looked almost identical to what came before 2015. News articles ran headlines describing an underwater volcano on the verge of blowing, drawing comparisons to a ticking clock buried beneath the Pacific Ocean. For a volcano that posed zero danger to anyone, it managed to capture an impressive amount of public curiosity and attention. Behind the headlines, scientists explained their reasoning carefully. The seafloor had risen close enough to the old threshold that, at the current pace of inflation, crossing that final stretch seemed likely within a matter of months rather than years. The math pointed toward one clear answer. Picture watching a bathtub fill almost to the very top, water climbing steadily toward the edge. Based on how fast it has been rising, you could reasonably guess it will overflow sometime soon. That confidence, built on years of careful measurement, is exactly what fueled this new deadline. Yet even as researchers stood behind their forecast, they added a quiet note of caution buried in their public statements. Volcanoes, they admitted, rarely behave with perfect predictability. Pinning an exact date on something happening deep underground always carries risk, no matter how strong the pattern looks beforehand. That caution turned out to matter more than anyone expected. As 2025 wore on, the volcano's rise toward its threshold began behaving strangely, slowing in ways nobody had accounted for. The deadline that once felt so certain was quietly starting to slip away, month by month. 2025 came and went. The bold public forecast, built on years of careful data, and one previous successful prediction did not come true. Axial Seamount did not erupt, and the confident deadline scientists had set for themselves simply passed by, unfulfilled. For a project built entirely around proving that volcanic eruptions could be forecast in advance, this was not a small setback. The entire point of the 2025 prediction had been to show that the 2015 success was not simply a lucky guess, but a repeatable, reliable method. Nothing about this failure happened suddenly or dramatically. There was no single moment where researchers realized their forecast had broken. Instead, the deadline slipped away gradually, month after month, as the volcano's behavior quietly drifted away from the pattern everyone had expected it to follow. Inflation had remained fairly steady through the year, continuing its slow climb toward the old threshold, but the earthquake activity that usually accompanies rising pressure stayed unusually calm, far quieter than what had preceded past eruptions. That mismatch left researchers with a genuine puzzle on their hands. Picture watching that same bathtub creep closer and closer to overflowing, only to have the water level suddenly hold steady just short of the rim, refusing to spill over no matter how full it looks. Something was clearly holding this volcano back from repeating its old script exactly. Rather than hide the failed forecast, scientists chose to publish their findings openly, walking through exactly what had happened and why their earlier prediction had run out of time. That kind of honesty is rare in science reporting, but it revealed something important about how this whole process actually works. A single successful prediction, it turned out, had not unlocked some perfect formula for reading a volcano's mind. It had only proven that pattern recognition could sometimes work under the right conditions for the right stretch of time. The real question now became obvious. What exactly had changed inside this volcano, and why had its rhythm suddenly shifted after behaving so predictably for years? Somewhere beneath axial seamount, the steady rhythm that once made this volcano feel predictable had quietly broken apart. Back in the middle of 2024, the seafloor had been rising by nearly 10 inches a year, a healthy, confident pace matching what scientists expected from past eruptions. By late 2025, that same rate had slowed to roughly 6 inches a year, a noticeable drop that could not simply be ignored. Something inside the volcano's plumbing system appeared to be changing, altering how quickly magma was flowing up from deep within the earth. Scientists faced a genuinely difficult question. Was the magma supply itself slowing down somewhere far below the seafloor? Was pressure escaping through some hidden pathway nobody had detected yet? Or was this simply a normal wobble, a pause the volcano had shown before without anyone noticing at the time? Picture filling that same bathtub from a faucet that suddenly starts running weaker without anyone touching the handle. The water still rises but slower, and you are left guessing whether someone changed the water pressure upstream, or whether the pipe itself has partly clogged somewhere out of sight. Earlier records offered a small clue. Years before, right after the 2015 eruption, inflation had also slowed dramatically, dropping from a blistering pace down to nearly nothing before suddenly picking back up again in a burst tied to what researchers called a shift in the magma supply itself. If something similar was happening now, this slowdown might not signal trouble at all. It might simply be one more twist in a cycle that had always been messier and less predictable than the clean threshold model suggested. The trouble was, nobody could say for certain which explanation was correct. That uncertainty forced the scientist most closely tied to this volcano's forecasts into an uncomfortable position. After years of building public trust with one successful prediction, he now had to stand in front of the same scientific community and admit honestly that the ground beneath axial seamount had stopped behaving the way anyone expected. In a blog post devoted entirely to tracking this one volcano, geophysicist Bill Chadwick wrote something researchers rarely say out loud. Nothing about axial seamount looked like an eruption was coming anytime soon. Inflation remained steady, but the earthquake activity that should have grown alongside it stayed unusually quiet. That short, plain statement carried enormous weight. After years of careful build-up toward a confident deadline, the scientist most responsible for that forecast was now telling the public directly that the wait was likely going to stretch on much longer than anyone had originally hoped. Chadwick went further, openly admitting something few experts are willing to say about their own predictions. He acknowledged that his team had repeatedly pushed their forecast further into the future, adjusting the timeline again and again as the volcano failed to match earlier expectations. Picture promising a friend you will finish a project by Friday, then pushing that promise to next Friday, then the Friday after that, each time believing you have finally nailed down the real answer. Eventually, even with the best intentions, that pattern starts to feel less like precision and more like guesswork. Rather than hide from that criticism, Chadwick addressed it directly, admitting that constantly moving the goalposts risked undermining the very credibility his team had built with their earlier success. Being right eventually, he acknowledged, does not prove much if the method behind the prediction cannot be trusted. This honesty revealed something deeper about the entire project happening beneath axial seamount. Forecasting a volcano this way had never been a perfect science. It relied heavily on spotting patterns in past behaviour and hoping those same patterns would repeat, a method that works only until the volcano decides to do something new. Faced with a forecast that kept slipping and a pattern that no longer fit cleanly, researchers realised simple pattern spotting alone would not be enough going forward. To truly understand what was happening inside this mountain, they would need something far more powerful than counting earthquakes and measuring inches of rising ground. They would need to build a completely different kind of tool. Every time a scientist updates a prediction, some people hear something else entirely. That the expert must have gotten it wrong the first time. That reaction misses something important about how real science works, especially with a process happening a mile underwater, out of sight of anyone on shore. Think about a weather forecaster predicting rain 5 days out, then adjusting that forecast as fresh data arrives the day before the storm hits. Nobody accuses that person of failing at their job. New information changed the picture, so the forecast changed with it. That same logic applies here, under thousands of feet of freezing water. A doctor works in a similar way. Order a test and a certain diagnosis follows. Order a second test that reveals something new, and that diagnosis often shifts entirely. Good medicine depends on revising conclusions as better information arrives, rather than clinging stubbornly to an early guess simply to avoid looking uncertain in front of a patient. Volcano forecasting deserves that same patience. Predicting the exact moment axial seamount will erupt means predicting the future behaviour of a system buried far beyond direct observation, driven by moving magma, shifting rock, and forces still only partly understood even by the scientists who study it every single day. Picture trying to guess exactly when a pot of water on a stove will boil over, except you cannot see the stove, cannot see the pot, and can only measure faint vibrations travelling through a kitchen wall. Given limits like that, adjusting your guess as new vibrations arrive is not failure. It is exactly what careful science demands from the people doing it honestly. Chadwick and his colleagues understood this tension clearly. Publishing a missed deadline invites criticism, even mockery from people expecting perfect certainty from a field that has never promised it. Yet quietly burying the failure, or changing the story without an explanation, would damage public trust in science far more than an honest correction ever could. So instead of hiding from the missed 2025 deadline, the team leaned into it, publishing new research explaining exactly why their earlier prediction fell short and what fresh patterns might explain the gap between expectation and reality. That kind of transparency rarely makes headlines, but it represents science working exactly the way it is supposed to. Consider how differently this story might read if the team had simply stayed silent after their forecast failed. No new paper, no public update, just a quiet hope everyone would forget the original promise. That path would have been easier, protecting a few reputations from criticism. Instead, the researchers chose the harder path, the one where being wrong in public becomes part of the process rather than something to hide from. Every failed guess, once explained honestly, becomes a clue pointing toward a better method, something future scientists studying other volcanoes can build on. That willingness to show the messy middle of scientific work, not just the tidy final answer, is part of what makes this project valuable beyond one mountain in the Pacific. Somewhere out there, a volcano sits near an actual city, and lessons learned from every missed deadline here could eventually sharpen a warning that saves real lives. Buried inside that new research sat something genuinely exciting, a fresh pattern nobody had fully mapped out before. Instead of simply watching inflation crawl toward an old threshold, researchers began studying the relationship between two different signals happening at once, and the shape of that relationship turned out to be stranger and far more useful than anyone had expected going in. In December of 2025, Bill Chadwick stood in front of a room full of geophysicists at a major scientific conference and presented something new. Not another simple deadline this time, but a fresh way of reading the volcano's signals, one that treated the earlier miss as data rather than failure. For years, researchers tracked two numbers separately: how much the seafloor rose and how many small earthquakes rattled the caldera each month. Both climbed as an eruption approached, but nobody had closely mapped how those two numbers moved together, rather than as two disconnected stories. The new analysis changed that. Chadwick found that seismicity and inflation were not simply rising together in a straight line. Instead, the relationship behaved exponentially, meaning earthquake activity did not just increase alongside the swelling ground. It accelerated, climbing faster and faster the closer the volcano crept toward its breaking point. Picture pushing a shopping cart down a gentle hill. At first it rolls slowly, barely picking up speed, but keep it moving, and the incline steepens, and suddenly that same cart is rocketing forward far faster than it started. An exponential relationship works the same way, staying deceptively calm right up until it suddenly does not. That detail explains something that had puzzled scientists all through 2025. Inflation had stayed remarkably steady the entire year, climbing at a slow, steady pace, yet earthquake activity had barely budged, staying low and quiet for months on end, leaving the volcano looking calmer than the rising seafloor suggested it should. Under the old model, that mismatch looked like trouble, a sign the volcano had broken its own pattern entirely. Under this new model, it looked more like patience. The steepest part of the curve, where earthquakes spike upward alongside the swelling ground, simply had not arrived yet. Based on this new relationship, Chadwick offered an updated forecast. Rather than expecting an eruption before the end of 2025, his team now projected the volcano would likely cross its threshold sometime before the end of 2026, following the same exponential curve outward to its logical, math-driven conclusion. This was not simply another guess pulled from thin air. It represented a genuine step forward, a forecast built on the actual physical relationship between two forces inside the volcano, rather than a straight line drawn between two past eruptions and hoped to repeat a third time without adjustment. Chadwick openly admitted the team had repeatedly moved their forecast forward in time, and he acknowledged that pattern could look troubling if it kept happening without real progress attached. But this update was different, he argued, because it pushed the method itself forward instead of simply extending an old deadline. The next eruption, whenever it finally arrived, would become the real test of this new approach. Either the exponential relationship would hold, proving the model correct, or the volcano would once again slip past expectations, sending researchers back to the drawing board, searching for whatever piece of the puzzle still remained hidden beneath the waves. Even Chadwick admitted something uncomfortable about the math. Keep extending a curve long enough, and eventually any forecast becomes technically correct simply because time passed. Proving a model actually works means catching the timing right, not landing somewhere close to the truth by accident. That is why this exponential approach mattered so much to the wider scientific community watching from a distance. If it succeeded, it would offer something more valuable than one accurate guess about one quiet volcano. It would hand researchers everywhere a genuine tool, built from physics rather than hope. Pattern recognition can only carry a forecast so far. Watching two numbers rise together and guessing when they might cross some invisible line works well enough, right up until the volcano decides to behave differently than it did the last time anyone measured it. Scientists needed something built on sturdier ground than memory alone. So a new project began, one designed to move past simple pattern spotting towards something closer to true physics. Rather than only comparing today's numbers against yesterday's eruptions, researchers built a computer model meant to simulate the actual physical processes happening deep inside the volcano, piece by piece, in real time. This model pulls in far more than just inflation and earthquakes. It accounts for how magma physically moves through cracks in the rock, how gas escapes from that magma as pressure builds, and how stress spreads through the surrounding crust as the chamber below slowly fills. Each of those forces gets folded into a single connected simulation. Picture the difference between guessing tomorrow's weather by remembering what happened on this same date last year, versus building a full simulation of moving air, ocean temperature, and pressure systems swirling across an entire continent. One method leans on memory, the other tries to recreate the actual physics driving the outcome. Feeding real-time data from the cabled observatory straight into this model lets researchers test their simulation constantly, adjusting it as fresh readings stream in from the seafloor. Rather than waiting years to see if one forecast holds true, scientists watch the model's predictions shift and sharpen almost immediately. What makes this project matter beyond one lonely mountain in the Pacific is where it might travel next. A model built and tested successfully on axial seamount could, in theory, get adapted for other volcanoes entirely, ones sitting far closer to cities, airports, and communities that cannot afford a forecast built on guesswork alone. Volcanoes near population centres rarely offer scientists this freedom to experiment. Every wrong guess there carries real consequences, evacuations that disrupt lives, warnings that come too late or cry wolf too often. Axial seamount, harmless and patient, gives researchers room to fail safely while building something that eventually will not be allowed to fail elsewhere. That is the quiet, larger mission hiding behind every headline about a swelling underwater mountain off the Oregon coast. This is not really a story about predicting one eruption in one remote patch of ocean. It is a story about learning to read the warning signs buried inside the Earth itself, tested here first because here, being wrong costs nothing but pride. Engineers building this kind of model face a genuine challenge most people never consider. A volcano does not hand over clean, simple numbers. It offers noisy, tangled signals, earthquakes mixed with ocean currents, pressure readings blurred by tides, patterns that need careful filtering before they mean anything useful at all. Sorting the real signal from the noise takes years of trial and error. That patient, unglamorous work rarely makes headlines the way a dramatic eruption forecast does. Yet it forms the true backbone of everything scientists have learned from this volcano, quietly building toward a future where similar tools might one day protect a coastline far more crowded than this empty stretch of the Pacific ever will be. Water boils at 212 degrees Fahrenheit. Every kid learns that number in school, a fixed rule of nature that seems impossible to break. Yet inside axial seamount's caldera, water regularly reaches temperatures past 700 degrees without ever boiling into steam, breaking a rule that feels like it should be unbreakable. The trick has nothing to do with the water itself. It has everything to do with pressure. A mile beneath the ocean's surface, the weight of all that water pressing down is crushing hard enough to keep liquid water stable at temperatures that would instantly explode into steam anywhere closer to the surface. Picture a pressure cooker sitting on a stove, sealed tight enough that steam cannot easily escape. Trapped inside, water can climb far past its normal boiling point without turning to vapour, simply because the sealed lid keeps pressure high enough to hold it in liquid form. The ocean floor works the same trick on a massive scale. To put that heat in perspective, an oven set to its highest setting rarely climbs past 500 degrees, and standing anywhere near that open oven door for more than a second or two would leave a nasty burn. Water pouring out of these vents runs hotter than that oven by a wide margin, yet stays completely liquid the entire time. This scorching water begins its journey as ordinary seawater, seeping down through cracks in newly formed volcanic rock. As it sinks deeper, it moves closer to the magma chamber sitting below the caldera, absorbing heat with every foot travelled downward until it becomes something closer to liquid fire trapped inside solid stone. Along the way, that superheated water dissolves minerals directly out of the surrounding rock, stripping away metals like iron, copper, and zinc as it forces its way back upward through narrow cracks and fissures. By the time it reaches the seafloor again, it carries a heavy, mineral-rich cargo picked up during its underground journey. When this scalding, mineral-loaded water finally bursts back out through vents in the caldera floor, it slams into freezing ocean water sitting just above. That sudden temperature shock forces dissolved minerals to crystallize almost instantly, turning invisible dissolved metal into solid particles the moment hot meets cold. The result looks almost like billowing smoke pouring from cracks in the rock, dark plumes rising and swirling into the surrounding water before slowly dispersing. Scientists studying vents like these often describe the effect as smoke rising from a chimney, even though nothing is actually burning anywhere near the seafloor. That comparison to a chimney turns out to be more accurate than it first sounds, because these particular vents do not just release smoke like plumes into open water. Over years of steady flow, the minerals crystallizing at each vent's mouth slowly stack on top of each other, building solid mineral towers rising directly out of the seafloor. Some towers grow tall enough to stand well over a fully grown adult, built entirely from metal pulled out of scalding water, one microscopic crystal at a time, layer stacking on layer for years without any human hand touching the structure. What forms next, rising from the ocean floor like something out of an alien world, looks nothing like any structure found anywhere else on the surface of our planet. Scattered across axial seamount's caldera floor sit clusters of hydrothermal vents, grouped together into named neighbourhoods scientists have studied for decades. One cluster carries the name Ashes, sitting along the edge of the caldera at a depth deep enough to crush most vehicles built for the ocean surface. Another cluster, further across the caldera, goes by the name International District, a fitting title for a place hosting dozens of individual vents packed close together, each one pouring its own stream of scalding, mineral-rich fluid into the surrounding water at slightly different temperatures and slightly different rates. Walking between these two neighbourhoods, if walking were even possible under that crushing pressure, would feel a bit like touring two very different districts of the same strange underwater city, each with its own personality, its own chimneys, and its own community of creatures clustered around the heat. The chimneys themselves come in different shapes depending on the minerals flowing through them, and how quickly those minerals cool once they hit open water. Some grow tall and narrow, almost like natural smokestacks. Others spread wider at the base, building broader mounds that look closer to a lumpy, mineral-coated hill. Scientists studying these structures have given individual vents their own nicknames over the years, treating them almost like landmarks on a map rather than nameless cracks in the rock. One particular vent, nicknamed Mushroom, sits directly in view of a high-definition camera streaming footage back to shore every single day without a break. That camera has captured years of footage showing shimmering, distorted water pouring from Mushroom's peak, the heat bending light exactly the way a hot road bends light on a summer afternoon. Watching that live feed, researchers can track subtle shifts in flow, colour and temperature almost as easily as checking a weather app on a phone. These chimneys grow far faster than most solid rock ever forms anywhere else on the planet. A structure that might take a mountain range millions of years to build can rise here in a matter of months, fueled by a constant uninterrupted supply of scalding, mineral-heavy fluid pouring out of the crust below. That speed makes these vent fields a rare kind of natural laboratory in their own right, a place where geologists can watch rock literally form in real time, instead of studying stone that finished growing millions of years before anyone was around to see it happen. These chimneys are not permanent monuments either. Built entirely from minerals crystallizing out of hot fluid, they can collapse under their own weight, get buried beneath fresh lava during an eruption, or simply crumble apart after years of chemical stress wearing down their structure from the inside out. When a chimney does collapse, it rarely disappears for long. Fresh fluid keeps flowing from the same crack in the rock below, and new mineral deposits begin building right back up almost immediately, layer by layer, the same patient process starting over from scratch on top of the rubble left behind. That endless cycle of building, collapsing, and rebuilding gives this entire vent field a strange kind of permanence, even though no single chimney lasts forever. The heat driving the whole system never stops flowing, and as long as magma keeps churning beneath the caldera, this underwater skyline will keep rising, falling, and rising again, layer after layer, for as long as the volcano itself stays alive. Every living thing on the surface of our planet ultimately depends on sunlight. Plants capture it directly, turning light into food through photosynthesis. Animals eat those plants, or eat other animals that ate those plants, building an entire chain of life stretching back to a single source of energy, pouring down from the sky. A mile beneath the Pacific Ocean, sunlight does not exist at all. Not dim light, not faint light filtering through murky water, but total, absolute darkness, the kind of blackness that never once lifts, day or night, season after season, for the entire history of this hidden volcano. By every rule that governs life on the surface, nothing should be able to survive down here. No sunlight means no plants. No plants should mean no food chain, no energy source, and no reason for any living creature to bother showing up in a place this hostile, this cold, and this permanently dark. Yet axial seamount's caldera teems with life, clustered thickly around its hottest, most dangerous vents. Thick beds of tube worms sway gently in shimmering currents. Spider crabs pick their way across jagged lava rock. Fish dart between shadows cast by mineral chimneys rising from the seafloor like alien skyscrapers. The discovery of ecosystems like this, first found decades ago near vents similar to these, completely rewrote what scientists believed about the basic requirements for life anywhere in the universe. Sunlight, it turned out, was not the only possible engine capable of powering an entire food chain from the ground up. Instead of sunlight, this ecosystem runs on chemical energy pulled directly from the volcano itself. Superheated water pouring from hydrothermal vents carries dissolved gases and minerals, byproducts of magma reacting with rock deep underground, and those chemicals turn out to hold exactly the kind of energy certain microscopic organisms can use. Picture an entire town powering itself not with electricity pulled from sunlight, but with energy harvested directly from a factory's exhaust pipe instead, an unlikely fuel source most places would never think to rely on. That is essentially the arrangement powering every creature living around these vents. This alternate path to survival matters far beyond one hidden volcano in the Pacific Ocean. If life on Earth can thrive without sunlight, fueled entirely by chemistry instead, that possibility opens the door to imagining life surviving in far stranger places, worlds where sunlight never reaches the surface at all. Consider a moon like Europa, orbiting Jupiter with an entire ocean sealed beneath a shell of ice thicker than any glacier on Earth. Sunlight has never touched that hidden ocean, and likely never will. If life exists there, it would almost certainly need a power source with nothing to do with light at all. Scientists studying moons orbiting distant planets, places locked in permanent darkness beneath miles of ice, now point directly back to vents like these as proof that darkness alone does not rule out life. Every tube worm and every crab living around axial seamount becomes, in a strange way, a stand-in for creatures that might be swimming through an alien ocean scientists have never actually seen. At the very base of axial seamount's entire food chain sits something almost invisible to the naked eye. Colonies of microbes, single-celled organisms clinging to hot rock and swirling through vent fluid, quietly doing a job normally reserved for plants sitting under open sky far above. These microbes rely on chemosynthesis, a word built from pieces meaning chemical and creation. Rather than converting light into food, they convert chemistry itself, pulling energy directly out of dissolved gases pouring from cracks in the volcano below, a process no plant on the sunlit surface could ever manage. The main fuel powering this process is hydrogen sulfide, a gas that smells like rotten eggs and would poison most animals living on the surface within minutes of exposure at that concentration. To these specialized microbes, that same toxic gas works like a nutritious meal, packed with exactly the kind of chemical energy their cells know how to unlock and put to use. Picture a car engine built to run on gasoline suddenly discovering it can also burn a completely different fuel most engines would consider useless or even damaging. That is roughly the trick these microbes have mastered, thriving on a chemical cocktail that would be lethal to almost every other living creature on the planet. That toxic gas does not stay dangerous forever either. Once these microbes finish processing it, the byproducts left behind become far less harmful, quietly cycling back into the surrounding water and slightly changing its chemistry, a small but constant contribution these tiny organisms make to the wider ocean around them. Using that hydrogen sulfide, along with oxygen, dissolved in the surrounding seawater, these microbes build sugars and other nutrients from scratch, essentially manufacturing their own food supply out of raw chemistry, rather than harvesting it from something else that grew first somewhere else. In a very real sense, they are the true farmers of this entire ecosystem, growing food nobody else down here could ever produce alone. These microbial colonies grow in thick, visible mats, coating rock surfaces near active vents, sometimes stretching for yards across the caldera floor in shades of white, orange, and pale yellow. Under the glow of a submersible's lights, those mats can look almost like pale, shifting carpets, rippling gently as warm currents pass through them. Some vent fields host mats thick enough to blanket an area roughly the size of a school gymnasium floor, an entire hidden farm growing in total darkness, fed by chemistry instead of daylight, invisible to anyone except the cameras and submersibles built to withstand the crushing pressure down there. Larger animals living nearby depend on these microbes completely, whether they realize it or not. Some creatures graze directly on the microbial mats, scraping nutrients straight off the rock. Others host colonies of these same microbes inside their own bodies, forming living partnerships that blur the line between one organism and another entirely. That second strategy turns out to be especially important for one of the strangest, most iconic animals living around these vents, a creature with no mouth, no stomach, and no obvious way of eating anything at all, yet one that somehow grows into one of the largest, most successful residents living inside this entire dark, hidden world. Giant tube worms rank among the strangest animals living anywhere on the ocean floor. An axial seamount hosts thick, swaying colonies of them clustered directly around the hottest hydrothermal vents. Each worm lives inside a tough white tube it builds itself, with only a soft, feathery tip poking out into the current. That feathery tip, often coloured bright red from blood rich in iron, serves as the worm's only real connection to the outside world. No mouth exists anywhere on its body. No stomach sits inside it either. By any normal standard, this animal should have no way of eating anything at all, and yet it thrives. The secret lives inside the worm's own body, packed into a specialised organ filled with billions of the same chemosynthetic microbes found coating rocks nearby. The worm's feathery tip absorbs hydrogen sulfide and oxygen straight from the surrounding water, delivering both directly to its internal colony of microscopic tenants living just beneath its skin. Those microbes then convert that raw chemistry into nutrients the worm can absorb directly into its own tissue, completing a partnership so tight that neither the worm nor its microbes could easily survive without the other. Picture a tenant living permanently inside a landlord's body, cooking every single meal in exchange for rent paid entirely in gas. These worms can grow surprisingly fast for something living in a place this extreme, some stretching several feet long within just a few years of settling near a fresh vent, behaving almost like weeds racing to claim fresh ground the moment new lava cools enough to settle on. To picture that growth clearly, imagine a plant sprouting from a seed and reaching the height of a grown adult within a single school year, a pace that would astonish any gardener used to watching seasons pass slowly before anything meaningful changes in the soil. That growth rate stunned early researchers who expected deep-sea creatures living in such a harsh, cold environment to grow painfully slowly, the way most animals in the darkest parts of the ocean typically do, far from any warm, steady source of chemical fuel. Sharing the same neighbourhood, spider crabs pick their way carefully across jagged mineral-coated rock, using long, spindly legs to navigate a landscape scattered with sudden bursts of scalding water. Unlike the tube worms, these crabs actively hunt, scavenging for scraps and grazing directly on the thick microbial mats covering nearby stone. Spider crabs seem almost unbothered by the extreme temperature swings surrounding them, walking calmly between icy ambient water and scalding vent fluid that could badly injure creatures living almost anywhere else on the planet. Their bodies have adapted over countless generations to tolerate a range of conditions most animals would never survive crossing even once in their entire lives. Watching footage of this vent community feels a little like watching a bustling neighbourhood built around a single strange power source everyone depends on. Tube worms rooted like buildings, crabs wandering like commuters, and microbes working quietly underneath it all. An entire hidden city thriving on chemistry alone, sitting deeper below the ocean surface than almost anywhere else humans regularly manage to explore or even see with their own eyes. Not every creature living around axial seamount clusters near the scalding heat of a hydrothermal vent. Down at the volcano's base, far from the mineral chimneys and shimmering water, a completely different community of animals has settled into a colder, quieter stretch of seafloor covered in thick, soft mud, roughly 1,000 feet below the crowded, chaotic summit itself. Among the strangest residents down here is a creature nicknamed the sea pig, a type of deep-sea sea cucumber shaped almost exactly like its name suggests, plump and pink, with stubby legs carrying it slowly across the muddy bottom, in search of scraps drifting down from the water far above its head. Sea pigs feed on marine snow, a constant gentle rain of dead organic material falling from far above, sinking down from the sunlit surface layers of the ocean over the course of days or even weeks before finally settling onto the soft, muddy floor near the base of the volcano itself. Bits of dead plankton, tiny shells and drifting waste make up most of that steady falling supply. Picture leftover crumbs falling slowly from an enormous invisible table set somewhere far above, drifting down for miles through freezing empty water before finally landing where creatures like the sea pig are waiting patiently below. That endless, gentle rainfall of nutrients supports an entirely different food web from the one clustered around the hottest vents nearby. Unlike the tube worms and crabs thriving directly on volcanic chemistry, animals living at Axial's base depend far more on this steady trickle of material sinking down from ordinary surface ecosystems, connecting this hidden volcano to the wider ocean stretching thousands of feet above its rocky summit, a lifeline reaching all the way back to sunlight far overhead. Other unusual animals share this same quiet territory. Ghostly white fish drift slowly through the darkness, moving with none of the urgency you might expect from a predator hunting in open water. Delicate, translucent shrimp hover just above the mud, nearly invisible except for the faint glint of a passing camera light sweeping across the seafloor. This base environment also plays a crucial role for the cabled observatory itself. Instruments here track ocean currents, temperature, and the flow of nutrients moving between the open ocean and the deep sea floor, studying not the volcano's fire, but the cold, patient rhythms of the water surrounding it every hour of the year. Large-scale ocean currents pass directly through this region too, carrying heat, oxygen, and tiny drifting organisms across enormous distances every single day of the year. Watching how those currents interact with life settled near Axial's base helps scientists understand connections stretching far beyond this one volcano, linking it to patterns shaping the entire Pacific Ocean and everything living inside it, from the smallest drifting shrimp to the largest migrating whale passing overhead. Between the fiery chemistry driving life at the summit and the slow, patient rainfall feeding creatures at the base, Axial Seamount hosts two entirely different worlds stacked directly on top of each other, separated by little more than a mile of open water and one enormous mountain of solid volcanic rock rising up quietly between them both, connecting two ecosystems that otherwise share almost nothing in common. In April of 2011, Axial Seamount erupted for the second time since scientists began closely watching it, sending fresh lava spreading across sections of the caldera floor within just a matter of hours. For most of the ecosystem living nearby, this event delivered something closer to catastrophe than curiosity, a sudden total end to life, as it had existed just hours earlier that same day. One particular vent field bore the full force of that eruption. Before the lava arrived, this stretch of seafloor teemed with life, thick colonies of tube worms swaying in warm currents, crabs picking through mineral-coated rock, and microbial mats coating every surface within reach of the venting fluid pouring from below. Susan Kelly, a researcher who had spent years studying these vent communities up close, described watching the aftermath in stark terms afterward. An entire venting area, she explained, had become completely covered in fresh lava, wiping out everything that once lived there in what amounted to a matter of hours rather than the slow decades most ecosystems take to change. Nothing recognizable remained on the surface once the flow finally cooled and hardened into fresh black rock. Picture an entire neighborhood buried instantly beneath a flood of molten rock, Every building, every resident, every trace of daily life vanishing beneath a hardening black sheet within a single afternoon, with nobody given any warning and nobody given any chance to escape. That is roughly the scale of destruction lava flows brought to this one small patch of ocean floor in 2011. Unlike an eruption on land, no fire raged and no ash cloud rose into the sky above the waves. The destruction here happened almost silently, cloaked by a mile of dark, freezing water, visible only through instruments and cameras built specifically to withstand pressure that would crush an unprotected human body almost instantly on contact. For scientists studying this event afterward, the destruction offered an unexpected scientific gift, however strange that might sound given the scale of what had just been lost. Rarely does anyone get the chance to study an entire ecosystem's total collapse in such precise detail, capturing exact before and after conditions using instruments already sitting in place, recording every change as it happened in real time, second by second. That detailed record let researchers ask a genuinely fascinating question afterward, one that had never been answered with this much data before. If an entire community of animals gets completely wiped from the map in a single afternoon, buried under fresh volcanic rock with seemingly nothing left alive anywhere nearby, how quickly, if ever, could life possibly find its way back to a place this hostile, this dark, and this far removed from any ordinary source of food? Nobody expected the answer that followed. Instead of staying lifeless for decades the way many scientists predicted, the same patch of scorched, freshly hardened rock began showing signs of returning life almost immediately, kicking off one of the fastest recovery stories anyone studying the deep ocean had ever documented anywhere on the seafloor, in any ocean, at any depth. Months after the 2011 eruption buried an entire vent field beneath fresh lava, researchers returned to the same coordinates expecting to find bare, lifeless rock stretching in every direction. Instead, they found something that stunned nearly everyone involved in the study. A vent nicknamed the Snowblower, already erupting with visible signs of biological activity. This particular vent earned its nickname from the way it behaved after the eruption, blasting out clouds of white, fluffy material that looked strikingly like snow swirling through the water column. That material was not falling ash or drifting sediment. It was living matter, dense clumps of microbes already colonizing the freshly cooled surface. Picture returning to a forest completely flattened by wildfire, expecting scorched earth stretching in every direction, only to find thick green moss already spreading across the blackened ground within a matter of weeks. That is roughly the shock researchers felt discovering microbial life already thriving atop rock that had been molten just months earlier. These microbes did not simply survive the eruption by hiding somewhere nearby and slowly creeping back. Evidence suggested they were bursting up from deep within cracks in the fresh lava itself, pouring out of the rock in massive quantities, as though the volcano's plumbing had been seeded with life from somewhere deep underground. That discovery reshaped how scientists think about survival after a volcanic eruption in this kind of environment. Rather than depending entirely on new colonists drifting in from distant, untouched vents somewhere else on the volcano, some of this recovery seems to begin from microbial populations already tucked away inside cracks and pores, hidden beneath the surface the entire time, waiting quietly for their moment. Larger animals followed close behind, arriving in a predictable layered sequence researchers have now documented across multiple eruptions at multiple sites. Microbial mats appear first, laying down a foundation of food. Small grazing creatures arrive next, drawn by that fresh supply. Tube worm larvae drift in afterward on ocean currents, settling and building their tubes atop the newly formed volcanic rock. Scientists studying this sequence compare it loosely to how a construction crew tackles a brand new building site, one stage clearing the way for the next. Foundations go in before walls rise, and walls rise before anyone thinks about furniture, each step depending entirely on the one that came directly before it. Within just a handful of years, a patch of sea floor that once looked completely dead can transform into a thriving vent community again, nearly indistinguishable from ones that were never touched by lava at all. Given how permanent destruction on land can feel after a major eruption, that speed genuinely surprised even experienced researchers who had studied similar recoveries in shallower water for years. This resilience carries a hopeful lesson stretching well beyond one volcano hidden in the Pacific Ocean. Ecosystems built around extreme, unstable conditions, it turns out, can also carry an extreme capacity for bouncing back quickly. A lesson worth remembering the next time this same volcano's summit gets buried beneath fresh lava all over again, as it inevitably will. Volcanoes rarely stay silent, even the ones buried beneath a mile of ocean water. As magma pushes upward and rock cracks under building pressure, axial seamount generates a constant low rumble of sound, most of it far too faint or far too low in pitch for any human ear to detect directly without help. Hydrophones scattered across the cabled observatory pick up these sounds constantly, translating vibrations travelling through rock and water into signals scientists can study on a screen. Earthquakes register as sharp, sudden bursts. Fluid rushing through cracks produces a steadier hissing static, running quietly underneath everything else happening on the caldera floor. During active periods, before and during an eruption, this underwater soundscape grows dramatically louder and busier. Thousands of small earthquakes can strike within a matter of hours, each one adding its own crack and rumble to an already crowded chorus, rising from deep beneath the caldera floor. Some of these low-frequency sounds travel remarkably far through water, much farther than similar vibrations would ever carry through open air. Certain species of whale rely on exactly this kind of low-frequency hearing to communicate across vast stretches of open ocean, calling to each other from many miles apart. That overlap raises a genuinely interesting question researchers have started exploring in recent years. Could whales passing near this stretch of the Pacific actually detect the rumbling and cracking coming from an active volcano below, picking up on axial seamount's restless moods, the same way they might notice another whale's distant call carrying across open water? Picture standing in a busy city and somehow being able to hear a rumble of thunder from a storm passing hundreds of miles away, a sound most people around you would never notice at all. That is roughly the kind of long-distance hearing certain whale species carry with them through the open ocean. Nobody has proven that whales pay any special attention to these particular sounds, or that an active volcano changes their behaviour in any meaningful way. But the physical overlap between whale communication and volcanic rumbling remains a striking coincidence, one more small sign of just how connected life across the entire ocean truly is, even across vast distances. Even without solving that mystery completely, this soundscape offers scientists something valuable in its own right. By simply listening, researchers can track the volcano's mood without a single camera, capturing earthquakes and fluid flow purely through sound, a method that works just as well in total darkness as it does under bright artificial light shining directly on the seafloor. Sound also travels faster and farther through water than most people ever realise, roughly 4 times faster than it moves through open air on the surface. That difference means a single instrument listening carefully can pick up activity happening across a surprisingly wide stretch of the caldera without needing a camera pointed at every single crack. Every time headlines mention an underwater volcano stirring off the coast of Oregon, a familiar worry tends to follow close behind. Coastal residents picture towering waves crashing onto beaches, images borrowed from disaster movies rather than anything grounded in how this particular volcano actually behaves deep beneath the crushing pressure of the waves above it. Axial seamount cannot produce that kind of disaster, and the reason comes down to simple physics rather than luck or good fortune. Tsunamis form when something suddenly displaces a massive volume of ocean water all at once, typically through a violent earthquake, a landslide, or an explosive eruption punching through the seafloor. This volcano does none of those things. Its lava is thin and runny, the kind geologists call basaltic, flowing gently across the seafloor rather than blasting outward in a violent explosion. Picture warm syrup spreading slowly across a plate compared to a soda can exploding after being shaken. Axial behaves like the syrup every single time. Because the eruption spreads gently rather than exploding, it never punches a sudden, violent hole through the water column above it. No shockwave slams into the ocean, no enormous chunk of seafloor collapses instantly downward. Without one of those triggers, there is simply no mechanism left capable of generating a wave large enough to threaten anyone on shore. The eruption also happens far too deep and far too far from land to matter to coastal communities in any direct way. Sitting nearly a mile underwater and roughly 300 miles offshore, any disturbance at the summit gets absorbed and dampened by an enormous volume of surrounding ocean water, long before it could ever reach a single beach in Oregon. That safety extends to earthquakes as well. Even though axial seamount produces thousands of small earthquakes leading up to an eruption, none of them connect to the fault systems capable of triggering a major quake felt on land. The United States Geological Survey does not even actively monitor this volcano, precisely because it poses zero hazard to anyone living nearby. Compare that to a very different kind of volcano, one that sits directly beneath a city or along a heavily populated coastline somewhere else on the planet. There, an eruption's timing matters enormously, and a missed forecast could cost lives rather than simply disappointing a room full of scientists gathered at a conference. Volcanoes like Mount Rainier, looming over Washington state, or countless others scattered along crowded coastlines around the world, cannot afford the luxury of trial and error that axial seamount offers so freely. Every forecast there needs to be right the first time, with entire communities depending on scientists getting the warning correct. That safety gap explains something important about why this particular volcano earned such intense scientific attention in the first place. Researchers get to practice, experiment, and even fail publicly here without endangering a single life, all while building tools that could one day matter enormously somewhere far more dangerous, including a volcano sitting much closer to home for millions of people around the world. Nearly 2,500 miles away from axial seamount, another American volcano has been swelling with a pattern that looks strikingly familiar to anyone who has followed this story closely from the start. On the big island of Hawaii, Kilauea's summit has been rising and falling in a rhythm scientists find genuinely hard to ignore. The United States Geological Survey has pointed directly to this similarity in recent public statements. Kilauea's summit, they noted, has been showing an ongoing pattern of uplift closely resembling the same behaviour scientists track so carefully beneath axial seamount's caldera, thousands of miles away on the opposite side of the country. Both volcanoes share a similar internal engine, magma chambers filling with molten rock, gradually pushing the surface upward until pressure finally reaches a breaking point, and something gives way beneath the accumulated strain. Watching two very different volcanoes follow such a similar rhythm offers scientists a rare, valuable chance to compare notes across completely different environments. That comparison works both directions too. Everything researchers learned tracking axial's slow, patient build-up feeds directly into how they read Kilauea's swelling ground, and unusual behaviour spotted at Kilauea can just as easily send scientists back to axial's own data, searching for a matching signal they might have overlooked the first time around. Picture two separate clocks ticking toward the same kind of alarm, one hidden underwater off a quiet stretch of the Pacific coast, the other sitting in plain sight on a tropical island crowded with tourists, hikers, and nearby communities living close enough to feel real consequences when that alarm finally sounds. That contrast matters enormously. Kilauea's eruptions can send lava flowing toward populated areas, forcing evacuations and threatening homes and highways in ways axial seamount could never manage from its hidden perch beneath the Pacific. Understanding the shared warning signs both volcanoes display becomes far more than an academic curiosity when one of them poses genuine, real danger to people living nearby. Lessons learned from patiently tracking axial's slow, repeated swelling and its stubbornly unpredictable timing directly inform how scientists interpret similar patterns rising beneath Kilauea's own summit. A pattern spotted and studied carefully in a place with zero risk becomes a genuinely valuable reference point the moment a similar pattern shows up, somewhere people actually live their lives. This connection reveals something important about how volcano science actually advances over time. Individual mountains rarely get studied in complete isolation from one another. Instead, patterns discovered at one location ripple outward, informing predictions at other volcanoes that might look completely different on the surface, yet still share the same underlying physical rules deep below their summits. As both volcanoes continue their slow climb toward whatever threshold finally triggers their next eruption, scientists watching both sites gain something valuable neither mountain could offer entirely on its own: a broader, sharper picture of how swelling ground translates into genuine warning, tested twice over in two very different corners of the same restless planet. Every eruption at axial seamount does something far bigger than reshape one caldera hidden beneath the Pacific Ocean. Each time lava spreads across the seafloor and cools into solid rock, it adds a fresh sliver of brand new crust to the ocean floor, a small but permanent addition to the surface of our entire planet. This process sits at the heart of a much larger story called seafloor spreading. Along ridges like this Juan de Fuca Ridge, tectonic plates slowly pull apart and molten rock rises to fill the widening gap, constantly creating new ocean floor as older crust gets pushed steadily outward in both directions. Picture a conveyor belt stretching across the bottom of the ocean, with fresh material added at the centre and older material slowly carried away toward the edges over the course of millions of years. Axial seamount sits directly on top of that conveyor belt, adding new sections of belt every time it erupts. Scientists studying this process gain something valuable that dry rock samples alone could never offer: a genuine chance to watch new crust form in real time, rather than only examining crust that finished cooling millions of years earlier somewhere else on the seafloor. Most of the ocean floor formed long before any human being existed to observe the process happening firsthand. That head start matters more than it might first seem. Rock collected from an ancient seafloor can reveal what happened, but it rarely explains exactly how it happened, step by step, moment by moment. Watching an eruption unfold fills in that missing sequence in a way no fossilized sample ever could manage alone. Here, cameras and sensors capture the entire process as it unfolds, tracking how quickly lava spreads, how fast it cools, and how the surrounding seafloor shifts and settles once the eruption finally ends. That real-time record fills in details rock samples alone simply cannot provide, no matter how carefully scientists study them afterward. This tiny corner of the Pacific also connects to something far larger than itself, stretching across the entire globe. The same basic process building new crust here has shaped every ocean floor on the planet, spreading plates apart at similar ridges circling the Earth, quietly rebuilding the surface of the planet over stretches of time longer than the whole of human history combined. Understanding how that rebuilding actually works, piece by piece, at a single, well-studied location, helps scientists interpret similar ridges elsewhere on the planet. Places far harder to monitor closely, buried underwater too deep or too remote for any cabled observatory to ever reach. With the same level of constant detailed attention scientists give this one volcano. In a very real sense, this hidden volcano is not just erupting. It is quietly building the planet itself, one thin layer of fresh volcanic rock at a time, adding new ground to the ocean floor with every eruption, long before anyone standing on dry land ever notices a single thing has changed beneath the waves, thousands of feet below their feet. Somewhere on this planet right now, a volcano sits beneath a city nobody has evacuated yet, its magma chamber slowly filling in, a pattern nobody has fully learned to read with any real confidence. Unlike axial seamount, that volcano cannot afford a decade of missed deadlines, moved goalposts, and honest scientific trial and error playing out in public. Every lesson pulled from this one hidden mountain off the Oregon coast has been building toward exactly that moment: the exponential relationship between shaking and swelling, the new physics-based model tracking magma, gas, and stress in real time. Even the honest, public admission that a forecast had run out of time. None of that knowledge stays locked inside one quiet caldera buried under a mile of Pacific water. Each piece feeds directly into a larger, still unfinished project, one aimed at learning to read the warning signs buried inside any volcano on Earth, whether it threatens nobody at all or threatens millions of people at once. Picture a pilot logging thousands of hours in a flight simulator long before ever carrying real passengers onto a real plane, testing bold moves and learning from every crash in a space where failure costs nothing but pride. Axial seamount has quietly served that same purpose for an entire generation of volcano scientists. That patient, decades-long project has already produced one genuine success. In 2015, scientists correctly forecast an eruption before it happened, the first time in recorded history anyone had pulled that off with real confidence, rather than a lucky guess dressed up as certainty after the fact. Every stumble since then, every missed deadline, every quietly revised forecast has only sharpened the tools built for the next attempt. Science rarely moves in a straight line from confusion to certainty. It moves in loops, testing an idea, watching it fail in some small way, then rebuilding something sturdier from the pieces left behind. Somewhere down the road, this same careful, patient method, tested first on a volcano nobody needed to fear, could give researchers the confidence to issue a real warning for a real volcano, threatening real lives, buying a town precious days or weeks to prepare for something once thought impossible to predict. The volcano itself does not know it is teaching anyone anything. It simply keeps filling, keeps cracking, keeps swelling toward whatever threshold finally sets it loose again, indifferent to headlines, forecasts, or the researchers watching every inch of its slow, silent breathing from a station on dry land far away. But somewhere on the other end of all that patient watching sits a future none of us can see yet. A moment when a different volcano, one standing far closer to people who never chose to live beside a sleeping giant, starts showing the same signs axial seamount showed first. When that day comes, the difference between knowing and guessing could decide everything.